Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hey everyone, my name is Nurasan Lagifari. Today I'll be doing a resolution of an IT specific issue, or commonly known as solvency specified IT case. So I'll give you a bit of background of me. I'm a person that quite likes video editing. Like videos, shots, record them using our phones, and then put it in a video editor software which we will do some like cuts, filtering, transitions, editing some sounds, stuff, and then rendering it and uploading it as a video. So in the end, usually we students we tend to get to be given project to create a video. Example, there's like a material called Dinya. Sometimes we would get a video assignment where we shot some kind of like anything related to the material that we were taught before, and then you have to do it in like all in this a day. I use a software named Kden Live. So Kden Live is an awesome software. It's quite awesome. It's flaws, it's free, libre, and open source, which is one of the reasons that I use it. Probably because I'm on Linux. There's much no other good editors out there. But the problem that I have with Kden Live is that its render time is a bit too long for me. You know, the video is about 6 minutes long, but then I need 15 minutes to render it, which is about 3 times the duration. That is quite a lot of time. That's if you need when you want to render a 1 second portion of the video, you need 3 seconds of CPU time or say computer time to render it, which is quite terrible for me. But if we're talking about who's to blame, whether it's his Kden Live or my laptop, my answer would be my laptop. Because, well, my laptop is a potato laptop. It's not designed to render videos, designed for workload, like regular workload with no graphics card or anything. And it's quite expensive to buy a new laptop, so I'd rather just stay on this laptop with me. But can you imagine like this problem when you see it in a big picture? Like, can you imagine this problem happening in, for example, in a company? So suppose we have a company, a video editing studio that has to process a lot of videos at once. So here they of course have employees of video editors, each having their own PCs with their own external graphic cards and those overpowered hardware, which of course costed them a lot of money. If you sum this up, it will, you know, sum to a really high number of money. And I don't think they're going to have a good time searching the money for them to pay for them. So well, that's a bit of background for me. This, I propose a solution to this. So, let's say we have a server, a really, really powerful server with maxed out hardware, with multiple NVIDIA graphics cards, with multiple CPU cores, a lot of cores actually. And then you might say that, okay, this server gets used by a user. But then what if but because this is a server, of course, multiple users can access it at once. Awesome. Because can you imagine like each of these users they have their own laptop. The laptop might be potato like mine, but then because they're editing the video, like the editing is done in the server, they can have really quick speeds, fast as the server is able to handle those editing uh processes rather than doing it on their own laptops. This is what I call as server-side rendering, or SSR, not to be confused with regular SSR like XJS or something like that. It's like server-side rendering, but rendering is like for the videos. So let's say my potato laptop is having a hard time rendering a video. But then there's this big boy server coming in to help us. So we transfer the video, like not the transfer, but like give out the details of the video editing project that we have, and then just slap it onto the server, and then it could just render it nicely, and then we can just stream it in to our laptop. And our laptops don't have to process that much amount of like compute needing for the video to render, because it's all done in the server. All that our laptop has to do is to just receive it and then render it in time. That's quite awesome. Time. So, like this. We have a potato server that is having a hard time rendering. So we ask the server, please render frames from 100 to 100 to 200. Okay, sure. The server received it, and then it then renders it at an exceedingly fast rate. Well, when our laptops can just receive it at our end, and then just show it to the user without needing to do any computing, except for streaming and stuff. This idea has some really huge opportunities. But the fact that we can do collaboration to the next level. Like suppose we have a central server where every render happens, and then there are multiple video editors collaborate, like multiple video editors accessing the same server. For example, this is a person called Azim, this is me. Like we're connected to the same server, and so we can just hop onto the same file and use the implement a collaboration on the server, because it's done centrally. On a regular video editor software like regular like Kdenlive or After Effects, Adobe Premiere Pro, you'd need I don't think you're going to be able to do collaboration, except that those Adobe systems will have to spend a lot of resources implementing collaboration. But with this architecture, we can really easily implement collaboration, because everything is in one place. It's in the server. And then we can just pass in stuff over the wire on each of the multipliers, and then that's pretty much it. But you might be thinking, like, imagine a server, you know, it has some huge powers, but like, I mean, it's pretty good at rendering, but when you add a lot of things, a lot of workload to it, like communicating, storing the data, streaming it, and many more, I don't think the server is going to be able to handle that much load. I mean, the server is quite large. I mean, like, it could be quite large and quite powerful, but like, there is a certain limit where sometimes you can't just put everything all at once. So, I propose a solution to use multiple servers at once, or distributed computing, using the microservices architecture. So, what is a microservice, you might ask? Microservice. So here is a bunch of microservices floating together. One of this hexagon is a microservice. A microservice has one task. It only has one task and nothing else. For example, this microservice at the top, it has the function of serving the website something. Then at the middle, it has the responsibility to do some session management for the user, and the last one is for rendering it. The thing is that microservices, they communicate to each other. They are like contained. The features, the code, they are all contained in one microservice. So when, for example, I mean, like, when a microservice is just by itself, it cannot do anything except for the thing that it can do. But when we combine multiple microservices together, we could compose a system that is capable of doing large things, like complex things at once. Like for example, when a microservice is asked one microservice, like ask what the session, or maybe ask the take to image, and so on, so on. So microservices, they communicate to each other, and they can be distributed among multiple servers, which is awesome. The word distribute is perfect for our usage, because it exactly it gives us an image about the like how we want to distribute the load between our servers, because we're planning to do multiple servers at once. So here's my master plan on how to do it. We have a microservice called frontend. This frontend microservice job is to, well, serve the frontend for the user. It can maybe a static asset using a reactive view, and some things that pretty much is static for the user. Second is the real-time backend. Once the front end is loaded by the user, or like the front end is serving some static files to the user, the website is shown. So that front end that is received on the user end will connect to a real-time backend that will connect to a different microservice. This real-time backend purpose is to manage sessions. So like when a user wants to do things, it communicates to this real-time backend because the front end is just a static server. It doesn't do much. So you're separated to a real-time backend. Next is a database to store some data which could then be accessed by other microservices pretty much. The next is a file storage. Of course, a when we're building a some kind of video editor, we will need to store data, videos, images, or maybe other metadata files, and we also of course need the file storage microservice. And of course, one of the most important keys of having a video editor composed of entirely microservices, we need the renderer because it's the main job of a video editor. We need to render the video. So like when and also the next one is the render queue. So in a microservice architecture, there's this one pattern to use a some kind of queue like Kafka or RabbitMQ or something like that, so that we can queue jobs to the renderer. Because I'm imagining this renderer to not just be one, because that'd be stupid. You know, we have a lot of these servers, and then they can just be only one renderer because this renderer is like the one and only microservice that does that does a lot of job. So I'm guessing the renderer to be kind of a cluster of servers. So for example, we have a server like maybe we rented some kind of VPS on a Google Cloud or something. We made a lot of VM instances, and those VM instances will get attached to a some kind of NVIDIA graphics card, an external graphics card, and then each of them will be a renderer. So the good thing is that when we have a render queue here, we can just queue a render and then it will get spread across those renderers that has the great NVIDIA things. So here's the diagram of how the system works. Suppose we have a user that accesses the website, like the web app, through an endpoint, probably a load balancer, something like Nginx, to distribute load between front end microservices, which would then forward it to front end. The front end will then serve the static assets or like some kind of assets that is the purpose of the front end to the end user, which will then get loaded to a browser, be it Chrome, Firefox, Safari, or anything else, which in that front end code will connect to a real-time backend endpoint somewhere included within its code. This connection will turn to a WebSocket connection or a real-time connection. Regular HTTP requests does not suffice for usage because it's pretty much stateless and you can only request respond, and that's kind of uncustomizable. So what I want is a WebSocket where we can just where we can, for example, we can send multiple things from the client to the server, and then the server can send multiple things to the client, and so on, so on. So we don't only have not only have using regular HTTP requests, we can request respond. We can pretty much do anything we want with WebSocket. So at the time this WebSocket session is established, the client will log in to the server using a token stored. And then the backend will acknowledge the login if the token is right. And then the front end will ask to render a project that is specified with the ID. So for example, the user opens a project in their kind of web page, clicked on a project, and then it connects to the real-time backend, and there is a command to retrieve the project with the specified ID. So then the real-time backend, because its job is to just manage user sessions, it needs to get the project of the user database. So it fetches the data from the database to retrieve some project metadata. So from the user from the project ID given by the user, the real-time backend connects to the database to ask for the project metadata, like the videos attached to it and the actual data to actual. So like the real-time backend needs to know to be able to serve this project. Then, before returning a response to the user, it needs to receive the URLs of assets that is specified in the project metadata stored in the database, which will then give the URL endpoints of assets. Then the real-time backend queues a render to the render queue, using the assets given from the file storage previously. So, the real-time backend, asynchronously, it will send the project metadata with some of the assets included to the client, so that the client can start up the video editor UI, but there's no render yet because it's only like you can imagine like when you start to open your video editor and then it opens the user interface, but it's pretty much empty. That's like the image of it. So there's this thing called the render cluster that I was talking about. So I'm imagining like maybe the renderer could be placed on a server, like servers that actually have GPU acceleration or some external GPU so that it can render efficiently. And then so we have a lot of servers here. Uh, each have their own microservice of the render, and then it connects to the render queue, asking continuously, "Hey, is there any job that I could do?" So this pattern is called job stealing. So for every renderer, it will try to pull and pull and pull. Maybe not pulling, maybe a subscription might work, a pub sub technique might work better, but the point is this. Every renderer asks if there's any job, and then the render queue will then distribute the load. That's the cool thing. So for example, the render queue, it wants to render a frames from 1 to 100. So since maybe the render queue, no, not the render queue, maybe the real-time backend estimated that there would be, it would require a lot of processing power for just one renderer to commit to render 100 frames. It will need to distribute it across multiple renderers. So here in this example, we batch a render frame, a render request to a render from 1 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, and so on to other more renderers. And each of them will be given a tag so that it knows where to respond back. So each of these renderers will ask to the file storage to retrieve assets. You can see there are a lot of lines here because there are multiple renderers and it needs to each of them needs to retrieve assets from the file storage. So where they got their assets from, because back then in back then the real-time backend connected to the file storage to retrieve the project assets, which is valid when the renderers tries to retrieve the asset from the file storage. So the file storage then sends back the assets like video files, images, elements, and so on and so on. And then the renderer will start the rendering process. After it has done rendering, it will then send out or stream the rendered frames to the render queue. And then this quick page. Then the render queue then initiated a streaming a request to the real-time backend once like it has got its first few frames. And then next up, the real-time backend will then forward that streaming to the end user. So it gets received by the browser like Chrome, Firefox, or anything like that through WebSocket to stream that rendered video in real time. And then this process gets repeated and repeated and repeated over again because it's a video rendering, it's a video editor. For example, when the user wanted to play a video, like play, and then the real-time backend will send out render requests to the render queue. The render queue will then spread out to multiple render instances, and then the renderers will then contact the file storage to retrieve the assets, and then the renderer will render those frames, which will then given back to the render queue, and then the render queue streams it back to the real-time backend, where the real-time backend will stream it back to the user so that it can see the video in real time. like that. And that's pretty much how it works. I guess that's all from me. Thanks for listening. I hope you can get some insight about how maybe about maybe how distributed system works, and maybe give you an idea of how to create better systems. So for me, thanks for listening. Assalamualaikum warahmatullahi wabarakatuh.